All right, everyone, welcome back. So in this example, we will be dealing with the work and kinetic energy theorem, but in conjunction with a spring. All right. So specifically, this problem deals with the compression of a spring. Okay, so in this problem, this block here is dropped from some initial height above this surface. We don't know what that height is, and it turns out for this specific problem, we don't need it. All right, we're only worried about once this block strikes the top here, as the spring is being compressed, we want to answer these three things. Okay, so they are, in part A, what's the work done by the gravitational force? What's the work done by the spring force? And what's the block's speed just before it strikes the platform, right? We can figure all these things out during compression, okay? So let's dive in. Part A here, what's the work done by gravity? Well, work is always integral from A to B of some force, in this case gravitational force, dotted with the displacement. And so in this case, I'll use y because let's use down as our y direction, right? Our positive y direction. All right, so let's evaluate the vectors here, right? The gravitational force is pointing down. Let me go ahead and write that. So Fg is down, and during compression, the displacement is down. Well, I don't have very much room there. Let me do it over here. Right? Displacement. Well, let's not write d, let's write y. The distance y, right? Also, the other force during compression is the spring force. That's pointing up. Spring force. So, the force that will do positive work is the force that's pointing in the direction of positive displacement. In other words, down. Gravity is that force. Gravity will do positive work. The spring force will do a negative work. Okay? Gravity will try, it'll do its best to speed the block up and accelerate it downwards, right, towards the center of Earth. But remember that the spring force gets stronger and stronger and stronger the further the spring is from its equilibrium position. So eventually the spring force will overcome the force of gravity, right, and do negative work and compress it to a stop. Okay? After that, yes, the spring will, shoot the block back up, right? But that's a whole other problem. So, back to part A. We want to plug in now for the vectors. Oops, I'm still in blue. All right, integral from A to B. Again, point A is the initial contact. Point B is some, distance of maximum compression, some point down there. Okay. So, just so you know, force of gravity is mg in the y direction, y hat, and that's dotted with the displacement dy, which has a magnitude and direction such. All right. Evaluating, well, we have integral a to b of mg dy. Y hat dotted with y hat, they're the same vector, so cosine of 0 is 1. So now it's just time to integrate, and we have, well, mg times the maximum compression, y, right? And we know all of those values. The problem states a mass, a spring constant, and a maximum compression distance. So we're good to go. Mass of 0.25, G 9.81, and 0.16. So we should get a value of 0.39 joules. Again, a positive value. Gravity does positive work. In part B, the work done by the spring force, Well, spring force now, we have the same format, integral F dot some displacement, in this case dy. And now let's plug in. It should be negative, so let's see if that's what we get. Spring force is negative ky vector, integral a to b, dotted with the dy vector here, right? And so this negative comes from the fact that it's pointing up, which is in the negative direction that we've specified, right? So I'm going to pull the constants out front. We have integral a to b, and magnitude of y is just y, dotted with dy. I guess I didn't do that above. I don't need to do it here. I've done it in previous videos. So we have the magnitude is y times dy, and those are both in the same direction, so cosine of 0 is 1. And this will give us negative, okay, and then, over 2, that's right, and then yb squared minus ya squared. All right, now which one cancels out? Which one's 0? Remember, b is the final position, a is the initial position. Well, with springs, remember the equilibrium length or equilibrium position is usually the 0 position. All right, so that will go away. And we see that indeed it is negative. So 1/2 times our spring constant of 370 times yb squared. Yb squared? I don't know. Where is that? 0.16 squared. We should get a value of negative 4.74, if I did my math correct, joules. All right? It's negative. And so, good so far, good so far. Part C, how do we get the speed, right? We're dealing with work, we're dealing with the two forces. Where does speed come into play? Well, if you read the title of the example, it comes from the work kinetic energy theorem, which hopefully you know by heart by now. Part C is the work, in this case, the total work is delta K. All right? And the total work comes from the work from all of the constituent forces. And so during compression, there's only two forces right there. So guess what? We simply add up the work from those forces. So we have the work from, that's a sloppy W. Let's try it again. There we go. Work gravity plus work spring, right? I'll put the minuses in there momentarily. And that equals delta K, which means it's the 1/2 m times the change in speeds squared. Right there. All right. And so from point A to point B, B is the final, A is the initial. Which one cancels out? Well, if it compresses to a stop, right, momentarily before stopping, that means point B, that speed is 0. It compresses to a final speed of 0. And that means that the speed at point A is what we're trying to solve for, right? And that's the same as the speed of the block just before it hits, right? Just above, a micrometer above that platform, right? That's the speed. What this says is that the change in the object's kinetic energy, and that comes from the block and the spring, that change is from some maximum to 0. Well, that changes because there is some work being done on it. So let's see. So we have work gravity was 0.39 minus, or adding the work from the spring. We actually have a leading negative here. Let's hope the left side is negative. It looks like it will be. What value is that? Negative 0.35? 4.35? So solving for VA, right, the speed at VA gives us divided by the mass of 0.25 and square root of all that. Whoops, negative in there. There we go. That way the calculator, it doesn't scream at you. We get that. We should get a positive speed of about 5.9 meters per second. Okay, so this was using the work kinetic energy theorem, and it worked out, right? We get a positive speed. And so again, what this means qualitatively is that because there was a positive change in kinetic energy, right? Sorry, because there was a negative change in kinetic energy, right? Negative. It went from some initial speed down to zero. It decreased speed because there was a negative work being done on it, right? You can say that another way. There was a positive work. Well, yeah, sorry. There was a negative work being done to decrease its speed down to zero. Okay. In essence, this is using the work kinetic energy theorem to solve for a final speed of an object. Thanks for watching.